This spring fascinates me. I'll completely uncoil it, except for a few kinks. Now, watch as I put it in hot water, 75 degrees or so. Rapidly, the spring reforms. Isn't that stunning? This spring is made from nitinol wire. The name comes from the elements that comprise it and where it was discovered. It's a shape memory metal, which means it returns to whatever shape it had when formed at a high temperature. A length of this wire was formed at a higher temperature into a spring and then cooled. No matter how it's bent at lower temperature, it will, at high temperature, return to its original shape. Here's another example.
Here's a piece of that same wire all scrunched up. At high temperature, when it was formed, it was straight. So when I put it in hot water, it almost instantly unwinds itself. That's so amazing to me. Let's watch it again.
There are some clever uses for this wire. For example, this device has fascinated me since childhood. It's a type of engine.
It's very simple. A large, small wheel, each grooved on their side,
with a loop of nitinol wire that runs through that groove and connects them.
To make it run, I just contact the small bottom wheel with water, which I've heated to 75 degrees Celsius. Then, spin the top wheel a bit, and the device then spins on its own. It uses the temperature difference between the water and the air to power the engine. When I remove the water, the engine stops spinning.
This engine runs because this loop of nitinol wire was originally straight at a high temperature. To see how that causes the engine to operate, watch what happens as I contact the lower wheel with the hot water. I'll mark the position of the wire on the left with a yellow line. When the wheel contacts the hot water, the wire moves to the left and it oscillates a bit. It's trying to straighten. Then, when I start the wheel, the wire's distance from the initial position is much greater. It's hard to see, so I'll mark its position with a purple line. This happens because when the bottom wheel comes into contact with the hot water, this section of the wire is heated.
If it were not in a loop, then the wire would be straight like this. But because it's in a loop, it tries to straighten, and in doing that exerts a force on the wheel, which causes it to turn. As it exits the water to travel to the top wheel, the air cools the wire, and the top wheel curves it again. It returns to the bottom and hits the hot water, and again tries to straighten and spins the lower wheel. Almost from the day of the discovery of nitinol, it's been used to create engines, or more precisely, energy conversion devices. Since the first in 1966, there have been patent after patent, each design of astonishing ingenuity and cleverness. The nitinol wire is arranged in intricate patterns so that a temperature difference induces a shape change and causes a part to rotate. The toy engine I demonstrated comes from one of the later designs. It's by Frederick Wang, who simplified the design by using air cooling and a single loop of wire on two wheels. So why does nitinol have this memory? Let's start by asking why we have brittle things like ceramics and deformable things like the metal used in a paperclip. The ceramic piece is, of course, rigid. It doesn't flex. Apply too much force,
and it shatters. Contrast this to a metal like this thin sheet of stainless steel. You can bend it, and it doesn't break. It just springs back. You can deform it even more by putting a crease in it, and it doesn't break. If I crease it enough, of course, it will eventually tear.
You can see the fundamental difference if you look at the pieces of these materials. The brittle ceramic has a nice clean break, which could be glued back together.
The ends of the metal sheet, in contrast, are deformed and unable to be easily reassembled.
So, unlike a ceramic, the metal can flow a bit.
It's the underlying atomic structure and type of bonding that produces these two behaviors.
In a ceramic, the bonds are typically rigid and very directional, so the atoms cannot move. Only a catastrophic event like a hammer separates them. Well, in a metal, the bonds between atoms are not as directional. They allow the atoms to move a bit, which imparts to a metal bendability, allows it to be deformed.
We can see what happens by looking at the atomic structure of a metal. Like the ceramic, it's a crystalline solid, which means it's ordered in a way that the pattern of the atoms repeats. When I stress the metal foil by moving it back and forth,
some planes of atoms slip. It's not that a row of atoms slips like it's greased, but it's an intricate mechanism that requires small defects in the crystal, which allow the atoms to move only tiny amounts in response to an applied stress. So you see that for a material to be deformed, but not fractured, requires that its atoms be able to move to accommodate the material's change in shape without breaking.
At least to a point. As we saw with the metal sheet, it will eventually break.
How the atoms in a shape memory material accommodate deformation is the key to understanding why it has a memory. I mentioned that planes of atoms in a metal can slip, but there's a different way that atoms can move to allow a metal to deform. Let's look at a simplified version of the atomic structure of nitinol, but one that captures the essence of why it has a memory. Its atomic structure at high temperatures is a nice, tidy, highly symmetric structure with the atoms arranged on the corners of squares. It's composed of small grains of this crystalline solid. At this temperature, it can be shaped into whatever form is useful, a spring, or as for the engine, a straight wire. When it cools, the crystal structure changes slightly. Notice that it's very similar. All the atoms are connected in the same way, but the nice tidy squares are now rhombuses. Notice that even though the atoms move a bit, the overall shape doesn't really change. So, for example, if you've made a spring, it still looks like a spring. This doesn't seem very exciting, but the structure has a unique property. It's composed of rhombuses that are mirror images of each other.
For example, notice the positions of the atoms on each side of this line are reflections of each other.
This is called a twinned structure. You can have all the rhombuses oriented this way, or this way. As you can now see, when the nitinol cools, it forms equal amounts of these two orientations of rhombuses, or of the two variants as they are called. What produces the memory effect in nitinol is that these variants can be easily changed from one to the other with very small motions of the atoms. For example, if I take the cooled nitinol and I apply a force, so I shear it across the top, you can see how it accommodates the stress not by the atoms slipping, but by changing the amount of each variant. In fact, at this point, it goes all to one type of variant. Now, the mechanism allows the nitinol to deform, but not fracture. The atoms can move a bit to accommodate the strain from stressing the material. You could picture many different stresses applied to the metal that will produce one of hundreds of types of mixtures of the two variants.
And many, many more in a three-dimensional structure.
But notice this. At all times, the atoms are connected in the same way as in the high-temperature phase, unlike in slip, where atoms can rearrange quite a bit more. So when the temperature is raised again, those rhombuses, no matter how they are distributed, return to tidy squares. The only structure that can result is the original structure, and so the nitinol reverts to the shape it had at high temperature. The utility of shape memory materials like nitinol aren't completely realized yet. It's used in some high-end products, premium eyeglasses that can be bent and twisted yet return to their original shape, or in designs where reducing weight is critical. For example, in the 2014 Chevrolet Corvette, a nitinol device replaced a heavy motorized actuator to open and close a vent in the car's trunk. And some medical uses, stents, for example, that expand once they are worn by the body. Although fascinating, it isn't a perfect material. It's expensive to produce and difficult to machine or to shape accurately. But by understanding how nitinol's memory works at an atomic level, researchers might be able to create new alloys that overcome these problems. I'm Bill Hammack, the Engineer Guy.